All right, class, this lesson is on torque converters. I am putting a video up, or I have a video up, I should say. I really want you guys to watch. This is a video of an instructor at a university teaching his class on torque converters. He's teaching it essentially how I was going to teach it in the classroom. As a matter of fact, when I was going to teach it in class, I probably would have had a handout, but it would have been all hands-on visual. There wouldn't have been PowerPoints because being able to see a torque converter taken apart is very helpful in seeing how it works. So we'll kind of go through this PowerPoint, but I really want you to watch that video because it really makes it easy to understand how torque converters work. Our basic objectives, we're going to identify and describe the components of a torque converter, explain how the torque converter works. We're going to talk about the parts and operation of torque converter clutches. This is our lockup torque converters that I've talked about in other lessons that are in basically every transmission now. We're going to talk about the stall test for torque converters, and we'll talk a little bit about the service of torque converters, but not a whole lot there. So our torque converter, as we've talked about, is located between the engine and transmission, and it is bolted to the flex plate and hooked. The housing of it is bolted to the flex plate. The other end goes into the pump of the transmission. And then the internal parts is what hooked to the input shaft of the transmission. And we'll talk about that. Okay? It is that link that transmits and multiplies the torque from the engine into the transmission. We'll talk about how it transmits it and how it multiplies that torque through what we call fluid coupling. Because if you remember our very first transmission, the Hydra-Matic in the Oldsmobile in 1940, it wasn't a torque converter. It was just a fluid coupling. It could not multiply torque. Okay? So that's why it wasn't technically considered a torque converter. Many people probably still call it a torque converter, but in actuality it couldn't multiply torque. All it was a fluid coupling. Okay, so this torque converter, what it does, so it multiplies and transmits the torque from the engine to the transmission, and then at slow speed, especially at idle, it allows a lot of slippage through this fluid coupling. That is what makes it possible for the transmission to be engaged in gear when the vehicle is stopped. As you know from manual transmissions, or should know, is that if you don't push down the clutch when you come to a stop in a manual transmission, it will kill the vehicle, because we are using the wheels and the brakes to actually stop the engine, because the engine is mechanically locked to the transmission in a manual transmission. In an automatic, the slippage in that torque converter is what allows us to come to a stop with the transmission in gear. That slippage means very little torque is being transmitted from the engine to the transmission. The three major parts of the torque converter are the turbine, impeller, and stator. Now we have the housing that bolts to the flywheel, and we have the part that goes into the pump, which also is where we find the impeller is in that part, and then the stator inside. Okay, so if we start with the stator, sometimes they call it the reactor. Almost always you're going to hear it called the stator. and it has a one-way clutch, and it is mounted inside of the torque converter. And it actually splines onto the stator support of your transmission. That's why it's important to watch that video, because you'll be able to see that, what that stator support looks like, because it's very similar on all transmissions, and where it splines on to that in that torque converter. This through the stator, and we'll talk about that. That is the member that actually is used to multiply torque. In our early fluid couplers, they didn't have a stator. That's why there was no torque multiplication. The impeller is the driving member and rotates with the engine. So the impeller is part of the housing, what they call the converter pump. So the part that mounts to the flex plate is just housing, and there's a weld part if you look at a torque converter, and the front part of the torque converter where it mounts into goes into the transmission. The impeller is part of that housing, and that's why they often call it the converter pump. But that's where the impeller is, and it is what the engine actually drives and rotates, and so that's the driving member of the torque converter. Okay, now we have the turbine. Okay, if the impeller is the drive member of the torque converter, the turbine is the driven member. The impeller is part of the housing of the torque converter, so it turns with the engine, where the turbine is not, where it's on the engine side, but it's not mechanically locked to the torque converter housing. It is actually able to turn or freewheel in there on its own. But the turbine is splined onto the input shaft of the transmission. So the impeller, being the drive member, picks the fluid up and pushes it into the turbine. That fluid through these veins is what locks these two members together. And again, that video shows you very precisely how it does that. But it's kind of like two fans facing each other. If you have two fans in your house and you put them right next to each other, one you have turned off, one you have turned on. If you turn one on and those fan blades start spinning, the air that it's pushing will start spinning the fan blades of the other one. That is how the torque converter works. There's blades or veins in this impeller and turbine. So the impeller picks the fluid up, pushes that fluid to the turbine, and so like the fan is pushing air, the impeller is pushing fluid, it hits the turbine and then starts to spin the turbine. Okay? That fluid is then directed back through the stator and hits the impeller and helps spin the impeller. And we'll talk about that a little bit more. But that's essentially the three parts of our torque converter. Here's kind of a picture of it. As you can see, the impeller is turning, picks up that fluid through these veins, pushes it, and these are really close together. Here they're kind of spread apart in this picture just so you can see, but these units are very close together. So it picks that fluid up, pushes the veins on the turbine, which is linked to the input shaft, so it turns the turbine, as then it's got power going into the input shaft of the transmission. Okay. That fluid then comes through the veins of the turbine, hits the stator, redirects it, and puts that fluid, starts pushing fluid back into the impeller. So essentially that helps push the impeller, which, if you remember, is directly hooked to the engine. So it's assisting, essentially, pushing that engine. So you're getting extra power to push that engine. So that's how you get torque multiplication. You're adding torque essentially to that engine through this system. Okay, now we're going to start talking about the different operations, different, maybe you might call them modes that we see in torque converters. And we've kind of already talked about torque multiplication, how that happens. Fluid is going from the impeller to the turbine, through the stator, back to the impeller. We get torque multiplication when the impeller is moving faster than the turbine. The impeller is what's hooked to the engine. The turbine is what's hooked to the input shaft. Okay? There's a one-way clutch in the stator. When fluid hits it in a certain direction, that one-way clutch is locked in place. Okay? So it helps push that fluid into the impeller, thus pushing the impeller, multiplying torque. Okay? Most vehicles' torque multiplication, passenger vehicles, is the 1.68 or 2.1 to 1. In other words, they're almost, in many vehicles, doubling the torque that is put into this transmission. That is why you see most drag racers use automatic transmissions. We do not get torque multiplication with manual transmissions. We do get it with automatic transmissions. As you can see, here's kind of a breakdown of the stator. Fluid comes in. If there was no path, if there was no stator, you can see the path of what the fluid would take. But with a stator, that fluid changes direction and hits the impeller to help push the impeller and multiply torque. Next phase is our coupling phase. This is when the turbine speed reaches about 90 to 95% of the impeller speed. So torque multiplication usually happens on heavy acceleration, heavy loads, like when we're first taking off from a stop sign, we're going to pass a vehicle. That gives us torque multiplication, helps us with acceleration. Coupling phase, we're up to speed, we're on a cruise, so we're not putting it under heavy load, so the speeds of the turbine and the impeller are pretty close. This is our coupling phase. Okay? In this coupling phase, the way the fluid hits that stator, it pushes it the opposite way, and this is why we have a one-way clutch. It allows the clutch to spin the other way. If that one-way clutch is not working properly, it's going to affect the operation of the torque converter, which we'll talk later. There's always some slippage during the coupling phase. Okay? This is normal, and in non-lockup converters, this was just part of the operation of the torque converter. In non-lockups, rarely is the turbine speed the same speed of the impeller. I can't think of really any times when it would be, because I mean it's not mechanically locked. We get a lot of fluid coupling, but it's not always perfect. Okay, so they don't turn the same speed. And when we get into lockup torque converters and diagnosing that with a scanner, we can actually see how much slippage is in that torque converter. Okay, and as I talked about, the difference in that speed between the turbine and the impeller is our converter slippage. Okay, then we have our stall speed, another operation of the torque converter. And this is the fastest RPM that the engine can reach while the turbine is held stationary. In other words, the input shaft of the transmission is not moving. We're able to spin the engine, but we can only get up to a certain speed before that coupling happens and essentially doesn't allow that engine to operate any higher RPM. It's starting to lock or hold that engine from going too much higher. And we will talk about how to test that stall speed at the end of this lesson. The next thing is we'll talk about creep. When you put an automatic transmission in gear, there's going to be, even at slow speeds, there's going to be some torque transmitted from the engine to the transmission. It's not going to be a lot, but there's going to be some, which if you do not hold your foot on the brake, it will want to creep that vehicle. Now, if you're on an incline, it probably won't. It'll probably still slide back. But on a relatively level ground, if you put that vehicle in gear and let off the brake, there is still a little bit of torque being transferred from the engine into the transmission through that torque converter, and you get vehicle creep. Okay, now that we've talked about the different modes or operating the torque converter, we've talked about non-lockups, how there's always some slippage there. We've talked about the different parts, impeller, stator, turbine. We're going to talk about torque converter clutches, and these are what we call lockup torque converters. There's another piece of equipment put in the torque converter to where in certain circumstances they can put a mechanical lockup to where it mechanically locks the engine to the transmission just like a clutch pedal, to where we eliminate that slippage. Okay, this happens during the coupling phase under those conditions, and it's mainly put there, first of all, to improve fuel economy, but also whenever we have slippage, we have heat in the transmission. When we're talking overdrive transmissions, we have gear reduction in overdrive, where we have gear multiplication or torque multiplication in lower gears. When we get into overdrive, we have actually torque reduction. If we didn't have a proper operating torque converter, that would put too much load on that clutch pack, and it would essentially burn that clutch pack up. It would cause it to slip. Combine that heat from that slipping, which the heat that's created in this torque converter, that's too much heat, and we'll end up burning up a transmission. Okay, heat is the biggest enemy of transmissions, and we've talked about that. We need to control that temperature. The torque converter, when it slips, is the greatest contributor to that heat. In many cases, the torque converter, even with lockup torque converters, are meant to slip. We would need that for torque multiplication or lower speeds. But when we get into coupling phase, especially cruise, higher gears, higher speeds, we can use that torque converter clutch to make a mechanical connection between the engine and the input shaft of the transmission. This clutch is a large disc, called a pressure plate or a clutch disc. Actually, when you look at it close, it looks similar to a clutch disc in a manual transmission. It has friction material. It has dampener assembly to it. The friction material, obviously, because it's got to take that clutch disc, apply it to the housing of the torque converter, It's the housing that's bolted to the flex plate. It uses fluid pressure to push on the back of that clutch, push against that housing. That friction material grabs that housing and locks the impeller, because the clutch disc is splined onto the impeller, and then we push fluid on the back of that clutch disc that then locks it to the torque converter housing. So now our impeller is mechanically locked to our input shaft and our engine. Okay. The dampener assembly with the springs is when it locks up, it doesn't hit really hard. It softens that engagement. Okay. So we don't, first of all, we don't get a real hard shift, and we don't possibly damage internal components of the transmission with a real hard engagement. Okay. This fluid that they're used to apply this clutch disc is controlled by a torque converter's clutch solenoid, and this solenoid controls the fluid flow, and this solenoid is controlled by the PCM or TCM. Now, if you remember, we had lock-up torque converters, 78 by Chrysler, that didn't use a solenoid, electrical solenoid. It uses a different way to apply pressure there. But in 79, GM, Buick came out with their electrical solenoid that applied pressure. This was before computers. They used some sort of load switch, usually vacuum operated, in the late 70s into the early 80s on non-computerized vehicles. So this load switch had electrical power that when the load got good enough, when the load was right on a steady cruise, low load, let me make that clear, a high load, they don't want to engage the lockup torque converter. A low load, higher speeds, we engage that torque converter. What they would do is they would have pressure switches in the transmission, so it would only apply voltage if it was in a certain gear, and then it would have a switch usually connected to some sort of load device, like usually a vacuum switch, that if it was low load, the transmission is in the right gear, voltage would go through the switches to the lockup solenoid, and the solenoid would work. But in most cases, once they got to computerized fuel injection, the computer took over the operation of the torque converter control solenoid. Here's kind of the breakdown, okay? If you look all the way to your left on the picture, that's your torque converter housing. That's what's bolted to your pressure plate. To your right, your converter pump assembly, that's our impeller. Remember, I told you that's another name for an impeller, is a converter pump assembly. Okay, that is welded to your housing. That way the impeller can always turn when the engine's turning. You see our stator in there. It really doesn't have a play in our lockup torque converter operation. But our turbine assembly, which is splined to the input shaft, is also splined to our pressure plate damper assembly. So they allow pressure, when they want to apply this, to come into the back side of that pressure plate, which would be on, if we're looking at this picture, on the right side, pushes that pressure plate, which has a friction material, into the converter housing and locks the impeller, which is hooked to the input shaft, mechanically to the engine through the converter housing. That gets us better fuel economy. It essentially gives us another gear, another step in our overdrive, to get us better fuel economy on the highway. because the engine will turn at a lower RPM. If we're talking about applying this, what happens is in a non-applied state, you'll have fluid pressure on the front side of that torque converter clutch. When they want to apply that torque converter clutch, they exhaust the fluid on the engine side of the clutch disc, and they apply pressure on the transmission side. That fluid on the driver's side actually acts as an accumulator, so it slowly exhausts as they're applying pressure. So it applies smoother and softer, but they exhaust the fluid on the engine side and apply pressure on the transmission side, which pushes that clutch disc and dampener assembly into the torque converter housing, which locks the impeller to the torque converter housing. And the impeller, as we know, is splined to the input shaft. Now, the fiber on this clutch disc, your early ones were paper, because remember, those torque converters were on and off. Applied pressure, relieved pressure. It's a basic fiber or paper. What we'd find on any of our clutch packs, clutch discs in our clutch packs that used to find. Newer transmissions, when they wanted to start shifting them smoother and softer, and they added pulse width modulation to where they gradually, that created more slippage. Paper elements would not hold up, so they started making them out of carbon fiber and Kevlar. There are year ranges where transmissions, I'll just point, a real common one is a GM, what they call 4L60E. There was years when the transmission looked the same, worked the same. The solenoid in one year was on and off. The next year they added a pulse width modulation. If you used a torque converter from the previous year, which would fit, everything would fit in, it would bolt up. If you used one with one of the paper friction material, it would burn up with the pulse width modulation because it applied it too slowly, it slipped too much, and the paper wouldn't hold up. So you had to make sure you had the right torque converter that had the carbon fiber or the Kevlar lining on the friction material. Everything else worked the same way. It's just once they started using pulse width modulation, they had to use a stronger friction material to hand up to that higher rate of slippage as they applied that torque converter clutch. Here's a picture of the dampener assembly. Again, if you've had a clutch pack, a manual clutch out, that looks very much like a clutch disc in a manual transmission. Those dampener springs are used so when it engages, it softens that engagement. Because remember, this dampener assembly, the clutch disc and a torque converter clutch, is splined to the impeller, which is splined to the input shaft. Without those dampener springs, it would be a pretty harsh engagement. In a powerful enough engine, you could actually cause engine damage if we didn't have those dampener springs. But at the very least, the customer would feel it and complain if that dampener assembly wasn't in there. Okay, the last thing we're going to talk about in torque converters is the stall test. I was thinking about waiting for when we go through the diagnostic systems, but I decided let's go ahead and do it now. This is a common test we do when we're trying to check the operation primarily of the stator in the torque converter. We usually do this when we have a low power situation, like it doesn't accelerate very well. We want to see if it's multiplying torque. And we want to see if the transmission's actually possibly even slipping if we put it under load. We need to be careful about this test. If you do this for too long, you can create too much heat and damage the torque converter or the transmission. We do this for a very short period of time. It's also to remember that when we're checking for performance problems of an engine, a lot of times when you're wanting to see if an engine will misfire if you put it under a little bit of load, we'll stall the engine up where we hold the brake, apply the gas. We want to do those for a very short amount of time. If you do it for too long, it creates a lot of temperature in that torque converter in a hurry. The slippage of that fluid, the torque converter slippage. Basic procedure, here it says connect a scan tool. If you have a tachometer, you wouldn't need to connect a scan tool. You can just watch the tachometer on the dash. You want all four wheels on the ground, okay? Is the most accurate way. We have done it when I'm trying to test other things where we've got it jacked up. But for the most part, we want the wheels on the ground. It says block the wheels. I mean, you don't necessarily need to do that. If your emergency brake didn't work, I would definitely block the wheels. But usually I just apply the emergency brake, hold the brake pedal really hard, and then do the stall test. But you start the engine. I usually want to do it when it's warm, and you want to see what the RPM is while you're sitting there running. Just kind of get you a base. All right, now that we got the vehicle ready, we've got the wheels blocked, emergency brake set. Both of those or one of those. The engine started up, it's running. It's usually preferably to do it when it's warmed up. Sometimes it's good to check it cold and warm. We're going to hold the foot firmly on the brake. That's got to be really down tight. Make sure nobody's standing in front of the vehicle. And then with the brake firmly set, here in this step it says reverse and drive. Reverse first, then drive. Usually I'll do drive and low gear. Maybe sometimes drive and reverse. The idea is in low gear reverse, pressure in the transmission is higher, so you could get a change in stall speeds. Look into your service information and see what they want you to do as far as what gear to test your stall speed in. And you're going to want to look at those specs of the stall speed to compare to see, make sure your transmission is operating properly. You can have bad stall speeds and it be connected to the engine. Engine power can affect stall speed. That's why you can have a spec, especially when you're doing aftermarket. A lot of times people will put higher stall if they put a performance camshaft in to get that RPM up, to get in the power range they want to get in. But the actual power of that engine will change the stall speed. Maybe at 1 horsepower, 1 power of the engine, it'll have a stall speed of 2,500. But a more powerful engine might create a stall speed of 2,800 RPM. Okay, so look at from that we know that if we have an engine in a factory vehicle that's not running properly and we have a lack of power in the engine, our stall speed is going to be lower than it should be. So performance of the engine can affect stall speeds. That's important to remember when we're checking the stall speeds, because most of the time we're checking stall speeds is because we're having an acceleration issue. The vehicle just seems to accelerate slow or has no power. And that's the main reason. Or we're checking to see if we're getting slippage in the transmission. So kind of some way we've completed our stall test. We're looking at the results. If all the stall speeds are within specification, everything's working. The torque converter's working, your clutch packs are holding, everything's good. If stall speeds are equal, if they're where they're supposed to be in specs between reverse and drive, but they're low, then you're most likely looking at a problem in your stator. The one-way clutch is slipping. It's not holding. So instead of torque multiplication happening, getting the RPM up where the impeller is moving faster than the turbine, the clutch is slipping, the one-way clutch in the stator is slipping, so the speeds of the turbine and impeller are able to reach the same speed quickly. So instead of slippage going on, coupling's going on, and the engine's not able to speed up. Okay. This is also where we, depend on what it's doing, we want to make sure our engine is operating properly. A plugged exhaust giving us low power is going to give us low stall speeds. I almost always, if I get a low power issue that I think may be connected to a torque converter that's not stalling up, I almost always check back pressure of exhaust first to make sure I don't have an engine performance problem there. Okay. If stall speeds are normal and the vehicle seems to accelerate well on getting up to speeds, but once it's up to speeds, you're having performance problems up to speeds, you could have a stator that is locked. So it is constantly trying to multiply the torque, and we're not getting proper coupling going on. So you could have a stator that's locked instead of slipping. Okay. Most common is that one-way clutch is slips, so we don't get torque multiplication, and we're getting coupling, and we don't get stall speeds where they're supposed to be. If, say, stall speeds are good in drive, but in low or reverse, they're not. Say it's supposed to be 1600, and we put it in drive, and we get 1600. But we put it in reverse, we get 2500. We could have a clutch pack or band that's supposed to be holding in reverse, slipping. There's an example where the torque converter is working, but we have something in the transmission not holding like it's supposed to. These are all reasons why we would run a stall test. Okay. So now that we've talked about our torque converters, and as far as service goes, when we're dealing with torque converters, say we go to rebuild or replace a transmission, we want to replace the torque converters. In non-lockup transmissions, a lot of times you can get by with not replacing the torque converter because there's not a whole lot that can go wrong. A lot of your 3-speed transmissions, that was pretty common. If we didn't have metal or damage where a bunch of metal got into the torque converter, a lot of 3-speed transmissions, if the torque converter worked well when we put the transmission out, we put the new old torque converter back in it. Overdrive transmissions where we have lockup torque converters, never reuse the torque converter because there's too much of a chance that friction material is bad or getting weak on the torque converter. So if we rebuild or replace a transmission, an overdrive transmission with a lockup torque converter, replace the torque converter. There are measurements you can do on a torque converter, but I always say if you have any doubts, replace the torque converter. There's no need, most of the time, shops don't have the equipment to hold things in place to where you can make sure everything's working and measuring and make the measurements in a torque converter. So most shops, if the transmission's rebuilt or replaced, you're just going to replace the torque converter also. So that kind of concludes our lesson on torque converters. So that kind of concludes our lesson on our hydraulic systems. Make sure you watch that video on torque converter. It's going to be very helpful to understand and see how a torque converter actually works. This is a major component of our transmission. It's important to understand how that works so we know how our transmission properly functions. So after you've done all the PowerPoints, watch the video, go ahead and take your quiz. That will complete this section. And then we'll move on to our next section, which is the internals of the transmission. We will talk about multi-disc clutch packs. We'll talk about bands. We'll talk more about one-way clutches because we'll find those in our internals of our transmission. We'll talk about planetary gear sets, and we'll talk about how all those work together to get power flow through the transmission and get the different speeds of our transmissions. All right, we will see you in the next lesson.